Hello, everyone, and welcome to this lecture of our course Reasoning LLMs from Scratch. So far, we have looked at what is the meaning of reinforcement learning, what are the different methods used in classical reinforcement learning, which are the tabular methods. Then we move to function approximation, how we can use function approximation methods if there are a large number of states and it is impossible to keep a tabular record of the value function of all these states. Then we slowly moved into policy gradient methods where we looked at can we directly find the optimal policy instead of looking at indirect methods which optimize the policy by using the action value function. And in the policy gradient methods, we first looked at the policy gradient theorem, which allowed us to calculate the gradient of a performance measure, and then that became the baseline from which everything else emerged. What is this everything? Well, firstly, we looked at our first policy gradient algorithm, which was reinforce. Then we looked at actor critic methods, in which there is a baseline subtracted from uh, the Monte Carlo return, and this baseline can be the value function itself. Next, we looked at how can we modify these policy gradient methods so that we don't allow our policy to deviate that much from our old policy or the base policy. And the first algorithm which introduced that was trust region policy optimization, which said that, okay, policy gradient approach is fine, but what happens is that if you don't allow the policy to restrict itself, sometimes you might have updates which can make the learning unstable. And this was being observed increasingly by researchers, and this trust region policy optimization became popular because it could impose a bound on the change in the policy. And then, building on the trust region policy optimization, we had proximal policy optimization, which said that uh, TRPO complications are more because the computations are tedious. It involves the inverse of a matrix, which is hard to calculate. So, can I have a best of both worlds? Can I have the simplicity of vanilla policy gradient methods? And can I have the trust region bound, which was introduced by the TRPO algorithm? And then this is where PPO was born. PPO essentially used a clip function to not allow the policy to deviate that much from the base policy, but it did not involve the KL divergence term at all. So the calculations became much simpler. In case you have not gone through some of these previous lectures, I encourage you to look at the previous three lectures which discussed on PPO and TRPO as well. Now we have come to a transition point in our course where up until now we were talking about reinforcement learning as a general method. Now what we are going to do is that we are going to understand how to use that method or apply that method to large language models. And uh, how reinforcement learning can be used to improve LLMs is an extremely interesting problem statement in itself, because at first glance it's not really obvious that LLMs can be represented as reinforcement learning problems. And the reason is that in reinforcement learning problems you have an agent which is interacting with the environment, receiving rewards and then improving. But how can LLMs be represented as reinforcement learning problems? When I was first thinking about this concept, it was not straightforward to me. In fact, I was not able to get through to understanding what are the states, what are the actions, what are the policy, what is the environment, even in this case. So, but afterwards, it became very much clear to me. And even though non intuitive, if you would have asked the authors of the classical book Reinforcement Learning and Introduction, Sutton and Barto, that do you think LLMs can be modeled as an agent environment? interface, probably they would have said no 10, 15 years back, because the problem itself is not very intuitive to cast it as a reinforcement learning problem. But as we will see, it's really not very difficult. It's straightforward to imagine these LLMs in this particular framework. Now, I'm going to move to a slideshow to help you understand how reinforcement learning problems can be represented, how large language models can be represented using reinforcement as a reinforcement learning problem. Okay, so in a typical reinforcement learning setting, you have an agent which is taking an action, and the agent is receiving a reward from the environment. And before the agent takes any action, the agent has a specific information which is called as the state of the agent. So, depending on the state of the agent or the information which the agent has received, it takes an actions and receives a reward. So this is the agent environment interface. Imagine if I am a chess player and I'm making a move, then I am the agent and my action is the move that I am making. And the state is the current configuration of the chess pieces on the board. And the reward depends on whether I win the chess match or I lose the chess match. If I win the chess match, my rewards are positive, otherwise, my rewards are going to be negative. So this is the agent environment interface, and these are the typical notations that we have been seeing from the beginning of this series. Now the question is that how do you adapt it to large language models? And we are going to look at what are the states and actions particularly. Now, firstly, here the agent is the LLM itself. The large language model is receiving some information, which is the state. This information can be received from either the user or the Python interpreter, and then the action is the uh, next word prediction which the large language model is predicting. So we are going to look at this in detail. Let's consider a specific example. Let's consider the prompt: Roger has 5 tennis balls and he buys 2 more cans of tennis balls. Each can has 3 tennis balls, and the question is, how many tennis balls does Roger have now? Now, the information which the agent has received is the prompt. So, the first state, which is S0, is just the prompt. And then, after the agent receives this information, the agent is going to take an action, which is the next word prediction. So, here the next word the agent predicts is Roger. Then Roger is again passed to the environment, and now the information is updated. Now the LLM has the initial prompt and Roger, so the action it takes is has. So the next action is has. Similarly, you can complete this for all the states. State S0 is prompt, state S1 is S0 and Roger, state S2 is S1 and has, state S3 is S2 and 11, and state S4 is S3 and tennis. So basically, what you are doing is whatever action the agent is taking, that action is getting added into the information which the LLM receives for the next iteration. So this is also like an iterative problem where the agent starts from state S0, takes action A0, moves to state S1, takes action A1, moves to take a state S2, etc. What we have done here is that we have cast uh, the act of answer completion as an agent environment interface where the agent is the LLM itself, and the answer completion is cast in terms of states and actions. So states is whatever information the LLM receives the up until the iteration. So information is the number of words or tokens which have been completed by the LLM up till that iteration, and the action is the next token or the next word which the LLM is predicting. So this way, the answer completion can be thought of as a series of states and actions taken by a large language model. Now that we have understood states and actions, what about rewards? Well, rewards is something which is also straightforward. The reward is going to depend on the quality of the answer. If my answer is correct, then I'm going to receive a positive reward. Otherwise, I'm going to receive a zero or a negative reward. So the rewards for all the intermediate steps is zero. The reward is only received at the end. This is quite similar to playing a chess game where you don't receive an you don't receive rewards for every move you make, but the reward which you receive is only after the game is won or lost. Similarly, here the reward the LLM receives is only after it has completed an entire sentence and understood whether the answer quality is good or bad. If the quality of the answer is good, the reward will be high. If the quality of the answer is bad, then the reward will be low. And this can be depicted in the traditional state action diagram where you go from S0, S1, S2, st, and then at the end, the LLM is receiving a reward. And depending on the reward received, then you update the LLM and make it better, make the predictions better. This is how the problems can be, or large language models can be cast as reinforcement learning problems with an agent environment interface. And the moment we do that, all the techniques that we have looked in the past suddenly become available to us because now we can represent this problem in the same format as is required for all the techniques that we have seen in the past. Now we are again going to go back to the notes and we are going to understand this a bit in terms of notations. Okay, so let's take an example here. The example I've taken is, let's say the prompt is I am going, and we are predicting the next word. So the next word depends on the previous word. So here the state is the combination of the previous three words, which is I am and going, and the action is the next word in the sequence. The reward denotes the coherency of the action given the input state, and the policy is the LLM itself. Remember, the policy is the probability of taking an action for the current state of the agent. The LLM does exactly that. Uh, Large language models are nothing but uh, models which give the probability of the next token, next best token given the current sequence of tokens. So the policy definition fits perfectly. Our policy is same as our agent, which is a bit weird that that never happens in other reinforcement learning problems. But in large language models, it's quite unique that our agent is same as our policy. Now, in case you are not familiar that LLMs predict the next token, have a look at this diagram. Here what we have receiving is that we are receiving the state which is the prompt and Roger, and the LLM has to predict the next word. So what the LLM does is that the LLM creates a word probability distribution for all the words in the dictionary, and you can see that has the maximum probability. So has is chosen as the next action. That's why LLM is same as the policy because it is giving us the probability over all possible actions. Okay, now some notations which are going to be important for us as we move ahead to the next lecture is the prompt is going to be denoted by X, which is made of a sequence of tokens. A token is a basic unit of a text. It can be a word or a single character. So, for example, if the sentence is I am going for a trip, the tokens are I am going for a trip, etc. So every single prompt is made up of a sequence of tokens. So X can be written as X1, X2, X3 X capital T, where T is the total number of tokens which we have in the given sequence. The completion is denoted by Y. So Y is the output text which is generated by model in response to the prompt. and the policy is denoted by pi theta. So, modern language models learn how likely a sentence is by predicting one word at a time based on all the words which came before it. For example, if we have the sentence, I like to eat pizza, initially the model will predict I, and the context will be just the prompt given by the user. Then the model will predict like given I. Then the model will predict to given I and like. Then the model will predict eat given I, like, and to. So now this can be expressed mathematically as the probability of the entire sentence is the probability of the first word, which is I here, the probability of second word given the first word, which is like given I, into the probability of the third word given the first word and the second word, etc. So this sequence continues. And in mathematical notations, this can be represented as probability of y given x for the given policy, where y is the completed answer and x is the given prompt, is the probability of y1 given x, the first token output, into the probability of y2 given x comma y1 into the probability of y3 given x comma y1 comma y2. So the entire probability is represented by a product of all this, and this product is denoted by the symbol capital pi. Now there is a notation which we use here where y2 given x comma y1 is also written as y2 given x comma y less than 2. Then this will be written as y3 given x comma y less than 3. This makes it easier for us to write down the notation. Instead of writing all the y's, we just say that whichever y's are less than 3, we are going to use that in this part of this sequence. So this is how the entire probability can be represented as. Okay, so now just to summarize, we have the agent, which is the LLM itself. The agent is receiving the state, which is the information, a set of a combination of the prompt given by the user plus the previous tokens predicted by the LLM. The action is the next token which the LLM is predicting, and the policy is the LLM itself. All of this we have seen two versions. One is the intuition, and the second is mathematical notation. Uh, in case the mathematics was a bit complex for you, feel free to pause this video and look at the maths again. It's straightforward. We have not done any significant complications in the math section here. Now, the question that you might ask is, Rajat, this is fine, but what about rewards? Who is going to give us the rewards? Remember, in the chess game, the reward was easy because I know if I won or lost. Similarly, if I am a small gazelle, a pet learning to run, then the rewards I am receiving from the nature are clear. I am either running or I am not. So the in most of the cases the rewards are clear to us, but in LLMs this is a challenge because it's not very easy to represent or get the rewards. Many of the rewards have a subjective quality to it because the answers given by the LLMs, many people might have different reactions to it. For example, if I ask an LLM to write a poem, then how would you rate the poem? Maybe some people like a poem, maybe some people don't like the poem. So in several instances the rewards are not objective but they are subjective rewards. So what people do is that usually these AI labs, including OpenAI, Google, Anthropic, etc., they ask you some questions while you are chatting regarding your preferences. Do you remember answering some things like this? This is something given by ChatGPT where it asks you which response do you like. Now, the reason it is asking this is because it is noting down your preferences for training a reward model, and this happens almost in a lot of these AI applications. It used to happen more before because we were trying to get the LLMs aligned to human preferences. And this entire process is called collecting human preferences. And then let's say I pick this implies that response 2 should receive a higher reward compared to response 1. So even though we do not have an actual reward model, we train a reward model based on the preferences that are collected from the users. So how is this training done? The training is done by collecting a lot of human preference data and then training a model. So the model receives this input, output for all of these human preference data, and then there is a training applied. So this is like a supervised learning problem, which is typical in predictive machine learning, where you have a lot of label data given and you have to fit a model which gives the output for a specific input. The reward model is trained to give higher scores for answers which are preferred more by humans. So if you have used apps like Midjourney, which are image generation apps, it gives you four different images, and maybe you select one, right? So that is taken as a reward. So that image receives a higher reward compared to other images, which is again used to train this reward model. So this is one crucial piece of the puzzle, which is having a reward model which is trained on human preference data, which is not available to us a priori. And this is what makes applying RL to LLM slightly more challenging, because the reward model has to be trained properly. So, this brings us to the end of today's lecture. It was a short lecture where we focused on how reinforcement learning methods, all that we have been learning so far, we now want to apply all these methods to LLMs. But to be able to apply it to LLMs, we need to cast the large language model problem, prediction problem, in typical reinforcement learning framework, which is the agent environment interface. Only when we do that, we can use the previous methods which we have developed for different uh, types of reinforcement learning problems. And in this lecture, we have successfully done that. We have understood what are the states, which are the combination of the prompt and the previous tokens given to the model. Action is the next token predicted by our model. Rewards are given by a reward model which is trained on human preference data. And the policy is nothing but the LLM itself, which is giving us the probability of taking of all the actions uh, given the state in which the agent is, which is the set of all the previous tokens. Okay, so this brings us to the end of today's lecture. Thank you so much, everyone. In tomorrow's lecture, we are going to cover uh, group relative policy optimization in detail. I have already released a video on that, which is a concise summary of GRPO. But in the next lecture, we are going to use the knowledge of everything we have seen so far, plus today's lecture, and understand the magic of GRPO. Thank you, everyone.